Okay, so Ramit recently completed his PhD thesis at Institute of Mathematical Sciences in Chennai, and his research interests include at the intersection of game theory and logic. Particularly, he also works on modal logic. So today he is going to talk about some results and some work that he had during his PhD. So yeah, please.
Good morning, everyone. I'd like to thank the IMSc for some of the. Let's get straight to it. Some central notions for logic. These two notions are very important for a logician. The notion of entailment of semantic group by sentences in a logic. So you talk about a model, which is this math M, which you talk about the sentence phi from this particular logic N, whether it is true or false in this particular model, and you have this entailment symbol. And you talk about derivability with respect to an axiom system AX. So you will be given a bunch of axioms, and you will be given a bunch of notions with which you can generate further truths syntactically. And if you are able to sort of derive from gamma, which would be a set of two sentences sentences in the logic that you have with respect to the axiom system, and if you're able to derive phi, you talk about say gamma derives phi from the system. With regards to my work, we will focus on the models in the context of game theory. We're trying to formalize certain notions from game theory, and the models that which will be inspired from would be say game descriptions, where we will talk about this normal for games. We'll talk about several games, which will be a more succinct representation of games in general. And in particular, we have two different classes of several games. We'll have something called a private description game, and another one called as the polymetric scheme. And then we'll also look into something called as class games. And apart from the game description, we'll also the models being game descriptions. We'll also look at models where you talk about an improvement graph that is built from a game description. For the logics, what we wanted to capture was certain path properties and certain node properties on the improvement graph structure. For capturing the path properties, we needed iteration as a operation present in our logic, and for which we had we use this logic called the least frequent logic, and also got inspired from this proposition dynamic logics, which had a diamond stars operator associated with it. So it turns out that the least frequent logics are undecidable, by which we mean that given a sentence in this particular logic, the question whether the sentence is satisfiable in a model, that is undecidable. We cannot have a procedure to figure out this.
So when you were saying least fixed point logics are undecidable, do you mean like some kind of A4 or restriction of A4 with the least fixed point? Like what?
So if you give the least fixed point iterated to it, then it would have the power to say encode the multi problem. So therefore you have the undecidable result. For the propositional dynamic logic, this is decidable, and we have a sound and a complete calculation of game classes with that.
So how is the propositional dynamic logic? It's like it seems like it's a subset of the A4.
It is a subset of the A4.
And what kind of operators or syntactical restrictions do you have in the PDL? It's not
okay. Syntactic restrictions.
Or maybe I don't know.
Okay, when we get to the syntax of it, I think from there you can obviously understand what we have. So the logic that we will actually look into, there are personal logic, the monadic is 6 point, and then we will extend this MLFP, this is called MLFP logic, with second order multipliers. Then we'll just extend the monadic nature of the 6 point iterator to be of a binary second order variable. So that will be like a binary 6 point quantifier. And then these MSO stat and MIQ stat, these are the propositional dynamic logic variants that I was talking about. We'll come to the descriptions as we go. There is a
So the second order quantifiers you mean on the sets you have.
On the sets, yes. So we will only be specifically quantifying certain sets. So we won't actually give it the full power of expressing any sets. So the results will be over models of improvement graphs of normal form games where you have fixed n players. You will use this logic LLP, and I have a polynomial time model checking algorithm for that. Then for the priority separable games, we extend the NLP logic with the second order quantifiers, with second order variables, for which we have one expressibility of Nash Equilibrium in the context of the priority separable games, and we also have a piecewise model checking algorithm for that. For the polymetric space, I have a result where we express the Nash Equilibrium in the context of polymetric space. For large games, we will be using it. I mean, it is central. Model will be only for these two logics. We'll show that for the exostrat one, you have an undecidable logic to express it. It aids in expressibility, but then it gives us too much expressibility for which the logic turns out to be undecidable. And for the MIQ strat logic, we will be able to have an axiomatization. We'll have completeness of this proof for that.
Sorry, what is the BLFP and
the BLFP
strats? What do they stand for?
So NLP stat is just a name. It's not, it doesn't stand for anything. BLFP actually stands for, say, if NLP was for the monadic least squared operator, BLFP would stand for the binary least squared operator. NSO stat and MIQ stat are just names. They will have a definition as we go along. It's the names that we have given in our paper. So this is not exactly a short name.
Ramit, sorry, just like I don't understand MLFP and so on.
Right, yeah.
So, yes. So I mean, like, can you just explain the first result to me? Like, what is like?
Okay.
If I don't understand logic, what is the first result?
First result. The first result is that if you are given an improvement graph of a particular game, where you say the number of players are fixed. Okay. So this improvement graph. Yeah, we will come to the following. So this is just a preview. I'm going to talk about that.
This is only.
Yes, I just wanted to set the audience on what I'm going to do. Sorry for confusing in. So yeah, I start off from here. So game theory and logic. What do we talk about? So this is actually taken from so this was from Bonanno in his survey that he had done for game theory and modal logic to alternative approaches. So over there, he's trying to classify game theory into 4 kinds of work game theorists are doing. One of them would be descriptive in nature, where he talks about there is this notion of what homo rationalis is, and in the descriptive form of game theory, they try to describe how this homo rationalis being behaves. And what is homo rationalis? Homo rationalis is the being that acts purposefully and logically and has well-defined goals. Has the desire to reach these goals, and importantly has the computing capabilities to be able to do so. They are basically a mathematical. So the way to think about them is they are the perfect abstraction of what human beings are in a certain sense.
When did he write this?
Okay, this paper. I think this was 1980s.
Much before AI.
Much before the
No, this is what will be survive World War III.
The other format is prescriptive in nature. So prescriptive is the form that we have the results of game theory as a template of how Homo sapiens and human beings would behave in a strategic interaction, how we expect them or how they should behave, right? So this approach to game theory interprets the results as being important, lessons being important, right? Then experimental is how I think most economists work with game theory. They focus on the human beings, and then they try to see how they behave in a collective, in a strategic situation, collectively. And there is also this other type of work that is going on in game theory, where we talk about the evolutionary. So we talk about, say, any solution concept. So there are different solution concepts in game theory, like Nash Equilibrium. We will look into some other concepts like finite improvement. So what these people who are studying game theory from the perspective of evolutionary lens, they will be talking about whether the iteratively people are making better choices or not. Okay. So, but I won't be talking about experimental evolution. My work would mostly focus on descriptive or prescriptive. They're not exactly also descriptive and prescriptive, but they give a flavor of these two areas. So I come to what improvement graphs are. Okay, so a normal form A would be of a two-way couple where you will first for n place where n is greater than 1, you will have sigma I, which will be a set of strategies, choice of strategies for each player I. Then you will have something called the set of all strategy profiles, which is sigma, which is the cross product of the entire strategies that each player could have chosen. Then you have the payoff for each particular player I, where you map a strategy profile to a real number, natural number. So this can be generalized to any partially ordered set. Like it can be any outcome. We need not have nominal chaos, even or cardinal chaos. It can be some values, some other things that have a partial order on this. Okay, some notational pointers. Each element of small sigma that belongs to the set of small strategy profiles are of this particular form. And notationally, we talk about say sigma minus I as the strategy profile without the element, without the strategy choice chosen by the I. You keep the rest of the players. Okay, so now what are improvement graphs? So improvement graph for normal form game. So this can be for any game form that you get. You talk about the set, you talk about the vertex set being all the strategy profiles. And you talk about these things called improvement edges for each particular player. So how are improvement edges defined? So you will, if you're given two strategy profiles, sigma and sigma dash, sigma prime, sigma improvement edge I, sigma prime will only happen if apart from the I player, everyone else chooses the same strategies that they had chosen. And for in particular the I player, there is a change that has happened, and the change is also beneficial. So there is a payoff that is greater that you get when you go from sigma to sigma dash. So this is like for a particular player, so this is not the correct way to state it, but for a particular player, you can think of it as from a strategy profile that he was currently stuck in, he or she was currently stuck in, they could sort of make an improvement by going to choose another strategy choice.
Is that procedure result in convergence?
So if it is in convergence, you will have a Nash Equilibrium. If it is not in convergence,
Right, so putting a recycling example. So these are the very more data analysis.
I mean, what happens when it doesn't happen? So it might have different other say solution concepts. Okay. And in general, so Nash talks about, so this is in the setting of pure strategy Nash Equilibrium. Nash talks about the setting where he talks about mixed strategies, where he talks also about not just we being choosing a particular strategy, but we also have a probabilistic distribution over all the strategies that we could have chosen. So in our setting, we don't exactly look into that. We have a pure strategy. So coming, I think someone had a question.
So this sounds very similar to like the notions of potential games, right? What you were describing, like you have
So I
from one.
this is the more general thing. It will everything else will actually. I mean, like all the. So I think this is the culmination of all the past research that has been done, and now you see this is as a general framework from which you can understand a lot of these other things. And
Actually, you will always have an application.
Yeah.
Here it is not like there are somebody else.
Just that he's restricting to pure strategies.
yes,
So in this graph, a sink will be a
pure. Yes. I think I have stated it right. Okay. So if you consider a subgraph with only one set of labels, if you think of this as a restriction where instead of all the n players, you only have a particular player talking. You only look at the particular player making the improvement move. Then you will have what you will have is a disconnected set of forest of paths of a particular length, or you will have sync nodes. You see. This is one, and the other thing is like it never has a cycle of edges having the same label, because if you are making the improvement, you cannot head back to the originals. But you can have a cycle where different people are making it. That is where we come. Okay, so just for illustration purposes, say these are the strategy profiles. These are for 7 agents. These are for 7 agents, and each of these agents have chosen. I mean, we have chosen one of the strategies from ABC, and I'm just showcasing that the rest of the agents are the same strategy choices, but they might, and only player 5 has a different strategy choice. It might happen that while making this move, certain other players have a different payoff change that has happened. Like for this is in case of player 4, you can see that even though the strategies are the same, in the second strategy, player 4 has a greater payoff. But we don't talk about this particular player. We only look at we only talk about this move in the context of player 5 making the move. So there are two things that we need to take into consideration when we see an improvement test. There is firstly the particular label that is associated with the edge, that is the player that is making the move. It makes a different strategy choice in the other vertex, and the payoff associated with this particular choice that it has made is greater than the previous vertex that it came from. So I'm just giving some examples of an improvement graph for a particular game, where we have a Nash Equilibrium over here, and this is a rock paper scissors game where you don't have Nash Equilibrium.
So the colors denote like which player has an
There is one. No, this is so which player is making the improvement. So I think I think the red color is for the second player and the blue color is for the first. So the properties of interest that we were looking into. So Nash Equilibrium is one of them. Then there is this property of the finite improvement property, weak, and then we have another weak finite improvement property, which we also call in the weak acyclicity. Okay. So to
The problem here is that I may improve, but then when somebody else improves, my cost may go up again. So
yes,
overall things.
overall things.
Yeah, that's a problem.
So I think so. You talk about a best response for a particular player. So what it would mean is a particular strategy choice for a particular player. So sigma I for the player I is the best response to the. So all my friends are also choosing some strategies. So if you look at the sigma minus I, like in the context of all these other people have chosen this, whatever strategy choice I choose, I do not have a better improvement. So this is my optimal improvement as of the move. So this is called the best response for a particular player. Nash Equilibrium would be one where all the players would be in such a status quo. No one would be wanting to like deviate to any other strategy profile because they are not getting a more payoff benefit by doing this. So this corresponds to the sync node as so path. So now in the space of all strategy profiles, this vertex set that we were looking at paths along from a particular vertex. So then you have this definition where you talk about the sequence sigma 1, sigma 2, where for each such transition that you make, a particular player makes the transition, and the rest of the players they stay at the same strategy choices. And that particular player also has a improvement that is associated with this. I didn't say that. That's what you want to do. But I actually wanted. This is actually defined. Rather, I should have not said this because of strategy progress. If I said on the improvement graph, then this would have.
Slide needs to improve.
Yeah, I'm sorry. The improvement path is a maximal path with this particular feature. So this corresponds to paths in IT. What I want to talk about is if in the game for which we have the corresponding improvement graph, we have all such paths as finite. So we are already in a finite description game. So the improvement graph will also be finite. The only way this improvement path is infinite is if you unroll the circle that you have for it to be maximum. So if you only have finite paths, then you say that the game particular game has the property of finite improvement property.
Every best response sequence converges.
Every response sequence converges. This corresponds. This is not a DAG to a DAG line when I is interpreted without the labels on its axis. And the weak acyclicity is from a particular strategy profile, you would be able to reach a Nash Equilibrium, but it is not guaranteed that always will exist.
Sorry, what is not guaranteed?
It is not guaranteed from all the strategy profiles that you will be able to reach a Nash Equilibrium, which was a guarantee in the finite improvement property. So now I come to what is logic.
For the existence of Nash Equilibrium is the weakest condition, then after that we have.
Yes. Yes.
You overcome this sense the finite.
So obviously the thing. So I'm not going to exactly discuss FO fully. I just want to, for the completeness, I've written all these things down. I just give examples of how we're going to use it. So we start off. So what mathematical logic, or I mean, like what logicians try to do is we want to capture the essence of the language with which we are expressing things. Okay. So in our particular case, we will be talking about the mathematical language that we talk about when we speak in respect to game theory. So FO can be talked in any context where the context you would need a vocabulary for which you would have this couple of you will have some relations, you will have some functions, you will have some constants, and then you will have this notion of sigma terms on this particular vocabulary. Yeah. I don't think I want to spend much time with this. I just say these are there, and this is how you build formulas in FO. You say there is some atomic formula over this particular vocabulary. You note it. That is one from this syntax. That is one of the formulas of FO. Then if you have phi as a formula, then you can have negation phi. So these are operations that you can add in and create new particular formulas. And if you have phi and if there is a free variable small x, then you can write something as radius x phi. Okay. This is the semantics of it. But I want to give you a feeling of something which people will be more comfortable with. So we talk about something like FO to express graph queries, where the vocabulary you would be talking about is it would contain E, which is the edge relation, which is the binary relation, and some sample graph queries. Sync. So for a graph to have a sync node, you say like for a particular vertex, it doesn't have any other edge, it doesn't have any other vertex to which it has an edge that it goes to. So there exists an x for all y, not of ex. Then you have a complete graph where you talk about, say, for all pairs of variables that you have x and y. If they are not equal, then they will have an edge between them. And then you have also this little slightly more complicated example of a query, the vertex cover of size at most state. You talk about, say, x different vertices. I mean, x possible different vertices where, say, each edge for all yz, each that is like on an edge y comma z, the y would either belong to one of the x1 to xk or z would belong to one of the x. Another example is where this notion of models, as we call it, or the semantic. So when we talk about, say, natural numbers and plus, so n stands for natural numbers and plus, and I'm writing down the formula for associativity that's present in this structure. So natural numbers and plus is called a structure where n is the domain of the structure, and so I'm hiding certain things over there in the representation work. We also talk about there being an interpretation function iota that has a polyfeature where the syntax of the black plus that we have corresponds to the addition that we talk about when we talk about natural numbers in the model. So in logic, what we are trying to do is like we are trying to delineate syntax from semantics. So you could have had the plus symbol being mapped to the multiplication symbol, but the multiplication operator in natural numbers. And we also have a valuation function for the first order variables where it will, for each of the first order variable, it will be mapped to some element from the domain of natural. And together, n plus iota and v make up what is called the model of natural numbers. And the formula that I've written over there is the natural numbers satisfy the property of associate for all x for all y, right? We have x plus 1, does that? You can also write it as. Okay. So this is what I was just saying in the previous slide. An example of something that is not satisfied. So if you have something like natural numbers multiplication and less than equal to 0, then you can talk about, say, does there exist an element whose square is less than 0, and it will not be satisfied in the model of natural. It will be satisfied in the model of numbers. Okay, so again, from F4 we'll talk about something called the second order logic system, where we turn to the variables that we were using, we were operating on. We will be looking at, say, variables that can be interpreted over subsets of the domain. Previously, they were only elements of the domain. Now they can be interpreted over the subsets of the domain. So therefore, in the semantic side, the only thing that we will change is for a model that satisfies there exists capital X phi. It would happen even only if there exists k tuple a subset A of subset of A, subset of BK, where D is the domain from which this is being borrowed, and K is the arity of the second order variable, like X is of arity. So we represent it as like n, where X is taking the value A, then it will be satisfying the formula.
Sorry,
Yes.
so by arity you mean the size of the set S that you can quantify over, or
No, by arity I mean the variable that we have, the X over here, they can contain so let me say.
there should be a chalk on the side of it.
So by arity I mean that this X will come in this form.
So can you just give me an example of a second order sentence?
Second order sentence.
Yeah.
So all of these have arity 1. So if E would be if E was something that I smuggled into my vocabulary, the edge of a graph,
Oh, I see.
this would be of arity 1.
So when I have a quantification about the relations, like so if you have a relation with some number of arguments, okay, how many arguments that relation
Yes,
has,
how many arguments?
and then he's saying that you can quantify about the relation.
Okay. Okay.
So these are some examples of the second order. So we talk about the equilibrium, where we talk about there exists some relation R, which will actually partition the vertex set. Then you talk about the equilibrium, where there exists some 3 different relations R to G, where each of these all vertices will either belong to the set R, the set P, the set G, or they will belong to one of them. That is basically what I write in this thing.
They belong to exactly one of them.
Exactly one of them. So now I come to what is MLP. Again, this is another you need to get used to before you see this. This is for definitional purposes, but I have an illustrative example to show this. Okay, so firstly, so there is something where we talk about even if you are given a vocabulary sigma, you smuggle in another monadic relational symbol R into this when you are trying to write down the formulas in reality. They are supposed to be monadic. So why so? And they are supposed to be also positively open. There are like 2 features that you need to when you're writing down the formulas, these are 2 things that you need to take care of. So the first thing is like the monadic nature. So for each of these formulas, you will be able to get an extract an operator associated with them. So like for instance, for phi, you will whatever formula you write down, there will be an operator f of phi, which will be a mapping from the power set of a set to the power set of a set, which will have this particular semantics associated with it. And the positivity restriction, this guarantee that the operator is mono. This is something which will be important because by natural Tarski's theorem, you would know that there would always exist an LFP, least fixed point, in case the operator is mono.
So what is the positivity restriction?
The positivity restriction would be So I think I've written it down here. Yeah. The positivity restriction is so this example that we have phi of r, you say like it's not a formalized, not a formal y, or not of ry, and this formula that we have over here. Okay. So the positivity restriction is this particular variable or the second order variable that we have. It will be under the scope of even number of negations. That is what we want. If it is under the scope of odd number of negations, it will that is not what we want. So
I'm not following what's happening.
yes, okay. So this particular formula R, I mean this phi of R, you have negation of x for all x for all y, not of ry for all y.
This is saying that there exists x and y
There exists x and y.
such that
So okay, but this is just this syntactically doesn't mean much.
okay.
Okay. Just to show that like this in this particular first instance, R comes under the scope of two negations. So this particular R is positive. Okay, and this particular R comes under the influence of 1, 2, 3 negations. So this is like negatively this negatively scoped R. So when we talk about a formula where we have only positively scoped second order variables, so they will always be under even if there are negations, when you write down when you expand the formula in this fully, you will always, I mean the negations will cancel out and you will only have the positively whatever that appears last as a positive instance in the form.
So should I think of it in the following sense? If you want a positive such PR, I sort of want to say that if I change my relation to only add more things, that can only make PR more.
Yes, this is what we want.
Okay.
So this is a syntactic way to carry this. And why? Because of this reason. We know that we do not have an effective procedure to test. We do not have an effective procedure to test whether a first order formula is monoton or not. So therefore what we assure is like when we are writing down the formula, in itself we write down only monoton. That is why we have that. So again, this is an illustrative example, but I think I'm running out of time because I have a lot of other things to do. I might come back to this if people want further.
What is LFP?
LFP. Okay, so LFP would be now if you have this so now you have this second order variable that you have in this particular formula.
Is it just a least fixed point?
It is the least point. And it is the least point of this particular the function associated with this formula that you have. Okay. This one.
So would you say once more, like why do you have so what is the need for the positivity? So I could understand that there is something in the fixed point.
Okay, the need for it. So the need for it is so if you just write down the formula normally, you would from the outset, if the formula is given from the outset, we would not know there is a result. Okay, so I would not be able to go through the details. So I also do not currently know the details of it. It says that there is no effective procedure to know whether this particular formula will use a positive, I mean, like an operator that I know. If for a particular formula phi, you have a operator f for phi. Whether that operator will be monoton or not, that we cannot know. So this is given. I mean, there is a result of this nature. Because of which we have to have this syntactic restriction where on the outset itself, when we are writing formulas, you will always guarantee monotonicity in the operators that are associated with it. So these are some of the formulas that we have written down in the field. So you can write on the same note. You can. I mean, we did not actually work on NLP. We also had mount operator associated. That is why that was there over there. But for the purposes of this talk, I will not complicate things further. Then this is a model checking algorithm that we had for this particular problem. So the input was a MLPC. In our particular case, it was an MLPC formula and sigma structure A and then interpretation rho. And then what you want to talk about is if this particular thing is true in this particular model, then this algorithm will output 1 or otherwise it will output 0. And this particular model checking algorithm follows suit from the FO standard FO procedure, we just have the added cases for the case of the count variable that we do, and the LPI arithmetic procedure. So, yes.
What do the M and the C in that MLFPC?
See, MLFP is what I was describing now, but I didn't give an example. Let's say, so we can do that later as well. The C is the count operator. When you talk about, say, there exists Z, we have a shortening. We can say like what do we mean by there exists at some RZ? We mean ki at least RZ is what if it is 2, it is satisfiable in at least one domain element Z, right? We can write down this thing in like there exists greater than 2 Z. So by which we mean that this particular formula will be true for at least 2 variables. So similarly, we can talk about less than, which will mean the only 2 particular, at most 2 particular variables. So we had a count operator for our particular purposes, and on that basis we had this result. So for the purposes of this talk, I don't think we need that, but I just wanted to this is what we had. And this was Jam and Sunil Simon and my paper, and we had the correctness of this model checking algorithm, where we have this particular and yes, sure. So QR is the quantifier rank of pi. Size of pi would be the length of pi. Yes, width of pi would be
And maybe how many conjunctions or
How many
conjunctions you have.
I mean, like, I think width of pi would be, I think you're correct. I'm just not exactly recalling right now.
Is A
What is A?
capital?
Oh, so capital is domain. So, I mean, like from the model that you're talking about, the domain of that. So you're talking about 83 part of QR pi, and for our particular formulas, the quantifier rank of this particular formula was always restricted to a number. So therefore, you have a polynomial type. So okay, fine. These are the technical games and
raised to quantify rank of pi, right?
So for our, so this is the most general setting. For our particular cases, the formulas that we always had, they were they only had say alternation with for all there exists. So we didn't have a say I mean like a list of n many of for alls or something. So therefore, we concluded this is a polynomial type in the particular improvement graph set.
So what are the interesting properties that you cannot describe if
Cannot
you
describe.
for all there exists? Or like,
So
because you were saying that you were restricted to only one alternation.
Right. So, and what are the interesting properties that we couldn't? So, the problem is we couldn't, but that doesn't mean we have a proof we couldn't. There is a difference, right? So, I was talking to you about this property called IE and PR, where what they do is like from a strategy profile, they are trying to take out, say, strategies of a particular player that do not aid in any improvement at all. Okay. So, it is like eliminating all the worst strategies that this particular player can have. Now, it is made for all the players. And accurately, from the improvement graph, they're throwing away strategy profiles and they're coming down to a smaller subset. Okay. In this process, you are supposed to reach a Nash Equilibrium, or you are supposed to reach correction of sets that will, I mean, that are like that way this particular reduction that is going to happen. But we couldn't write down for this. There is an iterative procedure that is happening, but we couldn't write down a formula that we put in our logic where we are not using more than 2 or 3 iterative, I mean like operators. So yeah, I mean there must be definitely more. This was just one of them where we got started, and I think I mentioned it later in the future scope. So separable games and MLFP. So here the motivation was like in the case of number theory, you have we wanted to have something. There is this thing called polymetric schemes, where they talk about the succinct representation on the class of games. And the succinct representation comes in the form of the P of function that we are given. They are thought of as now additively separable for a particular player with respect to another player. It's like a person playing a tournament. Okay. And then you compute all these partial payoffs and come up with the total payoff. This way. So what we wanted is to come up with a logic for which we will have a theory of polymetric space, and it turned out like the thing that we could have focused on was this notion of separability. Okay. So separable games would be where the only difference now is in this P of function. Initially it was for each particular player I. Now you have, say, for all players I and j, you are able to like have you are able to have an even more succinct representation actually. Like if you do the summation over previously pi was over sigma to pi. Here now pi is only over, say, like whatever the strategy choice for the particular player I and whatever the strategy choice for the particular player j, they will give some output, associated output. And the point was now to talk about from these partial results, you are going to compute a full P for this particular player. So this is any operation that you can do. It can be, say, it can be max, it can be an addition, which is actually what polymath is. Yeah, so exactly what I was trying to say. So Pi of S would be whatever this operator would be like a mean, max, or it would depend on these different settings. So again, I don't actually want to describe priority separable games because it would be a little complicated. I have a definition here, but I don't want to get into it as of the moment. I think I have a sketch of the thing. So over here, the other difference that I have is the players that are there, they're not just a flat structure, they also have a neighborhood structure amongst. So player 1, 2, 3, they are also related to all these other players. And the neighbors also have a ranking of order. Like for instance, so I talk about this example in the context of player 2. So player 2, the neighbors of player 2 being 1, 4, and 5. So the edges that are coming into player 2. And they are ranked as 1, 4, 5. And let us just assume like there are two strategy profiles S and T. And let us also assume like the partial pairs. So like player 1 when player 2 when it's competing against player 1, it gets a payoff of 2. Player 2 when it's competing with player 4, it gets a payoff of 2. And player 2 when competing with player 5 gets a payoff of 3. So similarly, you have this couple of partial payoffs for these two different strategy profiles. And you look into the lexicographic ordering of these fields. So this is a restriction that you look into. And if at some point it is greater, then you have a improvement. So okay. So the extension that we talked about here, so to model this now, the logic that we use. The second order variable that we talked about is this: you have the strategy profiles being included over there. Okay. Again, this is another definition that we have. The interesting thing is we are able to like sort of have these formulas over here which quantify against these particular pairs with its with the other player that it is playing against. And this is my NLP procedure, this alpha, where it will look at a minimum neighbor, and then it will just keep on the particular check across the list of transactions and obeying the ranking of those. So this is unpublished result. For this complicated Nash equilibrium that we had, we could write down the formula with our logic that we have had in a position. So basically, for arbitrary priority separable games, G, it has a Nash equilibrium if G satisfies this. It will be like a very complicated list of formulas that I have. If this is true, then the class of games that are satisfying this particular formula would be this arbitrary priority. That is what we talk about there. This is interesting. This is interesting because in this problem we have the algorithmic problem that we are actually modeling by this logic is this problem of checksum, which talks about being able to, which is a decision procedure of if you are given two lists of strings, whether you ask me whether the list one is lexicographically sorted with respect to the second string only. Okay. And in our exercise, we are able to capture this check sort kind of decision procedure. And this thing, I don't know, it was mentioned in a paper that I was reading. This is 5-page paper. So she said checkpoint is conjectured not to belong to d time n. D time n being the say so the languages which can be solved, the problems that can be solved in a Turing machine with time n. And she says this was conjectured by Quantic that this is not being done. So this I don't know yet, but since I think this might be something of interest to the audience here, so I brought this up. Okay.
Sorry, what is name?
N would be the so N would be okay. So N would be the input instance when you
Wait, so the input is 2 strings, is that correct?
the input is 2 strings of length. Yes. So N is from there.
N is the length of each string.
N is the length of each string.
And when you say lexicographic sorted with respect to each other, what does that mean? I mean,
That means that say is something like A, B, C, and A, D, C. So this is lexicographic. This is lexicographic greater than this one because on the second notional point, it has a it has a I mean like on this structure of alphabets. This is a greater lexicographic. So now we can, I mean, like for our instance, it is only 0s and 1s, and we only have like 0 is greater than 1, and we are only comparing against this. But the main the thing this is mentioned for any such strings of objects. Okay, so this particular logic will have a model checking in each case. We will have the same algorithm as before, but we now include the case for there exists y. This will if we solve the space time the recursion for the recursion problem for the space, we find it like it is in space. And for the lower bound, you will see that the complexity of echo is in space, and from there you can have a reduction. So that is really.
So when you say each space, this is like in the size of the graph. In
The size of the so this is written in the size of the game. So in the practice game, you are given a game form. On that particular game form, which is a succinct representation from in comparison with the improvement graphs. And on that particular game form, this will be to solve if you are given a MLP-C, I mean extended MLP-C formula. If it is true in this particular game form, to figure that out, we will need space amount of resource to have this algorithm check it.
Do you also have some hardness results on
By hardness, you mean the
whether the model checking problem is hard also? I mean,
so maybe this is complete, right? Like so has both, right? Like
oh, you show
I mean, like there is a
These are only each space.
no, it is upper bound key space. I okay, say key is so
I think at some point
it's a hardness. Yeah, my bad. Okay. So the next this bit is again, so we are just again generalizing from practice capabilities. We now have addition that we can do. So if you have addition you can do, then we have to have a binary relation over there, and that is why we did this particular thing. The only difference that we make from PLFP, we say that each particular second order variable that we introduce over here will have at most NP2. That is why you are talking about the binaries particular thing. And with this, we could write down this particular formula, which is again another iterative formula for capturing all the partial payoffs for each of these pairs and with the summation basically. And again, in a similar way, we have a result where we talk about, say, in this particular case, it will be like all polymetric scales will be satisfied by this particular formula. There exists a capital X Nash Equilibrium. Okay,
so we have around 10
10 minutes. Okay, so So this was on the front of least fixed point logics, and on the front of say the large games. So on the front of large games, what are large games basically? So now say like for instance, I think I can write it down faster than. So for all these players, if there are 3 players and they have chosen A all from them, so in a large game you see that the payoff is actually P for each other. This is the simplification that we need. Okay, that whatever I written down will boil down to this series. So like for instance, if there is 1 B, then it will be like 3 3 1 something like 2 2. So again, so we have large games over there, but we slightly modify the improvement notion over here for this particular case. We talk about players or teams making an improvement or discipline. And I have an example here. Okay, so this is a very interesting idea. So in large games, we talk about what we wanted to formalize was the notion of say each of these players will be influenced by another person making some choice. So we talk about something like we don't talk about another person, we talk about a coalition of a person. We say if half of or more of the population around me choose a particular strategy, then I should respond with another particular strategy, which might not or may not confirm or contradict the strategy in the context of it. So we wanted to formalize this particular sense, and for this we will and you could recurse on it in a certain sense. You say like if this is this particular player who thinks in this kind of a framework where he thinks like he wants to go with the majority of what people choose, let that person be of type T, then you can say like if another player might be if my population is of majority of type T, then I want to be of type not of T, which would mean he is of the contrarian person. Right? So okay. So then I have the syntax of this is where the MOSO stat and MI2 stat will come in. So before that we have so distribution constraints are this particular thing written down in a different form, but they are the same. And these particular formulas you will have for expressing the thing that I was just talking about. Like if you have a lot of people thinking in a certain way, then another outcome will be chosen. So this is the MSO stack quantification. This entire so you will have second order variables, you will have first order variables, and you are able to do something like alpha at x, which would mean that this particular player, whatever player you assign to x, chooses this category called alpha, and then you talk about p at x, which would mean a payoff of a particular player at this particular point. And so here capital X is actually a team of players, and you say the small player X belongs to this capital player team or capital player capital X. This is a type formula in this strategy. So this particular there is a motivation. So I've not done a very good job of explaining this, but whatever the thing that came about with this particular say logic, so the description of this logic is it turns out that this is an undecidable person. So we could express a lot with this, but we had run into we could sort of reduce an instance of the finite tiling problem to the finite satisfactory problem for the version of FOStat of FOStat. So FOStat just does away with the second order quantification. It just looks at the players firstly. And this is the finite tiling problem that we have for this reduction. So I think we can talk about this later also. This is what we do over there. So for each of these tiling instances, so this is the finite tiling game. You want to say at the start 0, 0, you want to have key 0 over there, and you want to say if there is an n such that at n cross n you can place in Tn and in such a way so that you can satisfy the vertex tiling constraint and the horizontal tiling constraints. So like for instance, in one particular corner I have T1, T3 and T2. So T1 and T2 satisfy the horizontal constraint and T1 and T3 satisfy the vertical. So the reduction that we talk about, we will map each particular point to a strategy profile over there, and each the tiling that we do over there in the strategy profile that will correspond to a payoff that is given by the strategy. So this is the overall picture of the reduction. I mean, after which we'll encode the tiling constraints into our logic. I mean, I have not written it down properly, I think, but this is again, this will follow from that. So this is Anand Padmanabha, Jam, and Greenberg. So undecidability of the finite satisfactory problem for Enosov stack. The satisfactory problem for the fragment of Enosov stack over model having a finite number of pairs is undecidable. So this is a micro stack where in the previous case we were talking about variables. We now replace it with constants. We say like their I is there in the particular representation, and this particular changes a lot in terms of say the logical expressibility, which is very interesting. So INJ are over the range C set of constants, and then you have this way of defining the logic. This is the syntax of the logic, and you have all the basic things that you were expressing before also, like Nash Equilibrium. So you talk about say all paths from a particular. So here the difference between the FO kind of work versus this one is for the modal logic perspective, we talked from a strategy profile. For the FO, we could choose any strategy profile. So for the propositional dynamic logics, we think of the improvement graph as a triptych model, and then from each strategy profile, we look at the edges outcome from it. We only talk about say all the reachability set from a particular strategy profile. We cannot talk about the entire improvement graph. So this is the limitation, but within this limitation, we have more, more properties of the logic that we. So first we have a bounded model property with this particular logic. So if the formula is of phi, then so gamma is the number of strategies that this particular game has, and then you can have a bound on this for each of the formula. It will satisfy in a model of this particular space. And so you do this procedure in the soundness and completeness of echo if you have seen those kind of things. So this is for the modal logic. You will have a list of axioms, and then you have a list of say inference rules, and on that basis you will be able to create a model out of it, and then you can check whether the formula is satisfied. It's a very long convoluted procedure. I have just given some instances of what are there at that point. So like for instance, we talk about say, so this should have meant that for each of the games, one particular strategy choice has been chosen. So this is like an axiom that you place into this when you talk about this particular satisfactory logic. Like another you have is like if a particular strategy profile led to a payoff of two, any path that you go along and you come across the same kind of strategy profile, you must have the same payoff. So we encode these kind of axiom schemas into this set of axioms. So these are only two of them. We have a bunch of them.
And you also do the soundness and complexity.
Yes. This is a complicated inference rule, but this actually means the proposition, this proposition that we have here. So this is as a proposition of the bounded pairs. These are non-theoretic conditions, and outcomes whatever it is. And two other results before I have. So this is the soundness and completeness, the first thing. And the second thing, this is again Ananta Jam's answer. We have a bisimulation equivalence for this particular object. So yeah, so there is this thing called LFP0. We want to get to what is LFP0. So in LFP0, they have what they do is this is a structural result for any formula in LFP. They are able to extract out, they are able to have a Solim kind of a representation where they take out the LFP quantifier at the end, and inside you will only have an FO form.
You mean a pre-next?
You mean a pre-next one. Exactly. So this is called that particular for given any formula at phi, you can construct this pre-next quantified extracted out formula LFP formula. This is called the LFP0. We want to see whether this can also happen for MLF. There is a slight caveat to why it cannot perhaps happen. Is because to go about this procedure, there is this entire theorem called the stage comparison lemma and all. Over there, they talk about getting to a negation normal form for a particular form, and to express that particular thing, they always need a binary quantifier. And I believe like we to have only monadic quantifiers everywhere, it might not be possible. So I don't know the answer to this question yet, but this is a question that I would like to further information on. So the stage comparison lemma is the bottleneck in this particular quest. This quest to represent IE here, the question that you asked, what kind of things can we not express? So we tried a lot to do this, but we couldn't, and but we do not also have a proof key we cannot do this. So this is a problem. So INDR is whatever I was trying to express is the you have a pure strategy, that is never the rest. And you try to eliminate all these such pure strategies. And then you take the game, and at each point you take out all these strategy profiles, and you reach a certain point where you cannot do any further equation. And the question was whether this particular entire process that we talked about can be represented in, forget all MLFP, can be represented in FOLFP logic. Forget MLFP. If I'm able to represent it in FOLFP logic, then also I know so I don't know an answer to this question. And this part I'm not, so I don't know, therefore that is why it is a question. So in the first example that I was talking about with regards to improvement graph, most of the variables, they did not only have a quantifier ordination of two quantifiers, they also had only two variables being used in the formulas. So then, say like for instance, we know FO2 is decidable. So I was asking whether what can we know about MLFP2 in that same period. Whether the iterative procedure that I was talking about that leads to undecidability is automatically encoded in this particular case as well or not. That is something that I have to check out.
So that undecidability proof, how many variables does it?
So that I have to check out. I don't remember now.
But okay, so that is your proof, right?
No, that is given. That is not.
Oh,
That is like a past result. Like people who are working on this thing, they figured this thing out.
that's 3. It was 3. Okay.
It was 3.
Oh, I see. I mean, this is you were saying about the FOML. Yeah,
Exactly. So this another is like so these are all syntactic restrictions can be get out. Like for instance, when we were talking about polymetrics and all priority sector whatever, we were having formulas of the form where there exists this 2 is representing a second order variable associated. So forward second order variable. Can we change this formula into one where we have forward variable, forward quantifier 1, where we talk about say first order variable, and exists one which is like a first order variable, and then you have a second order. So you have a bunch of first order variables, and then you have a second. Can we have something of this one, which will be reducing the complexity from this one, because here there are 2 set operators, so these will have more complexity versus this one. So these are things that we are searching for. We don't have an answer to them yet. Okay, thank you. I don't know. So these are the properties. And I would like to thank Sunil, Jam, and Ananta for the entire help for all these works that I've done. Yeah. And of course, like Abhishek Sankaran also. So he has also been very helpful in regards to this entire process.
questions. Yes. So I have a simple question maybe. So these when you have this quantifier alternation, so that hierarchy is kind of split, that should be easy to see, right? I mean,
So you're talking about the things expressible, right?
Yeah.
So that hierarchy is of course it's
Because it's like A4 plus. Okay, so Ramit will be around, so if you want to talk to him, so he's here today as well as whole of tomorrow, so he will be sitting in the visitors room. Okay, thank you, Ramit.